I'm going to say I alluded to this, but I didn't really allude to it. I just flat out said it. It's the same as it always was, except you're doing it a piece at a time. So if I want to find the limit for a vector value function, I'm going to find the limit for each piece of that vector value function. All right? If I want to find the derivative, I'm going to find the derivative of each piece of the vector value function. Antiderivative, same deal. All right? So it's really not that challenging conceptually, but you still have to carry out the process. All right? So if I give you something like a vector value function that contains a natural log and I ask you to find an antiderivative, and you don't know what the antiderivative of the natural log is, then you might have to integrate by parts. So the concept itself is not hard in that, oh, I just have to take the antiderivative of each piece. But then if you run up against something that is challenging to find the antiderivative of, then it's a different story. But we're not there yet. We'll get there in a couple minutes. Here it's just a matter of saying, I want the limit as t approaches 3. So I'm gonna apply direct substitution. So it's gonna be equal to 3 squared minus 3 times 3 plus 4 times I plus 4 times 3 plus 3 times j. So 4i plus 15j, 5 threes. So I'll pop a little star on number 2. Now number 3 has that little extra ingredient related to continuity. That one I'll take you through because people forget how to test for continuity. It was kind of a big deal for 5 minutes in Calc 1, and then it ended up not being a big deal anymore for a long time, and now it's going to be a huge deal moving forward. All right, whether a function is, I mean, most people remember the main idea. If a function is not continuous, it's not differentiable. All right, so we want to address continuity because if I'm interested in finding a derivative of a function, I want to know where the derivative is going to be relevant. All right, but it's kind of a lost art to determine what the actual values that are continuous or discontinuous would be. So we're going to find a limit as t approaches -3 of r of t, which is just plug and chug. So -3 time, comma, -3 squared plus 1. So -3, 10. All right. Now, independent of the concept of a limit, what I'm going to do is just evaluate the function r of -3. Now, if a function is continuous, it should feel like you're doing the same calculation repeatedly. You're like, I'm just doing the same thing again. Right? If that's the case, then odds are what you're dealing with is continuous. Right? So that's what's happening here. When I evaluate the function, I get -3, -3 squared plus 1. I get the same thing. All right. So for part C, the answer is going to be yes. And that's because the limit as t approaches -3 of r of t is equal to r of -3. All right. So that's going back to the process that really, honestly, this process I got from my Calc 1 notes. All I did was I copied and pasted it, and I changed my F's to R's, my X's to T's. You get the idea. So I took the f of x notation, made it r of t notation. That's the only difference, all right? Because you need to show that a point exists, right? If it's going to be continuous, the point has to exist, right? Because if it doesn't exist, there's going to be a hole, there's going to be an asymptote or something like that. You need to show that the limit exists, all right? Now you can have limits that exist, but they're not finite, all right? So the two sides of an asymptote, they're both going to infinity. The limit is infinity, right? So the limit exists, it just happens to be infinity. But what I need is that the limit, for the limit and the point that exists to be the same thing, right? So we're talking about two parts of a graph coming together at the same location, right? That's all this process is telling us, right? But now we're expanding it into the vector context. And so that allows us to expand it into 3 dimensions and 4 dimensions and so on, right? So it's taking something that we already know from Calc 1 and building on it, all right? Now, D is kind of sort of reminding us that the limit definition of a derivative is still a thing, right? This is kind of like a little piece of it. You know, f of x plus h minus f of x all over h. Okay? I don't really like spending a whole heck of a lot of time worrying about that in this class, but I do want to take a second and remind us that that is still a thing that can be done. All right, so we can substitute expressions into vector valued functions just like we can with numbers. All right, so instead of the t, I'm going to put a t plus 2. From that, I'm going to subtract r of t. When you simplify, you get 2 comma t plus 2 squared minus t squared. Now you can clean that up if you want, but it's not really necessary. It's really just getting at the idea that not only can you substitute numerical values into a vector value function, you can substitute expressions in. And if you can substitute expressions in, then the limit definition of a derivative would apply. If that's the case, then all the rules for derivatives and antiderivatives would also apply. Power rule, product, quotient chain rule, implicit differentiation, log differentiation, pretty much anything you can think of, all right? And then everything that goes with antiderivatives could apply. So integration by parts, partial fraction decomposition, just everything, all right? So unfortunately, that means that you got to kind of be prepared. I mean, more than kind of. You got to know your stuff. You got to know how to take a derivative or antiderivative. But that doesn't mean I'm going to beat you over the head with like one obscure antiderivative rule after another. But it is possible that you could have to integrate by parts for a question on a test. Right, so you got to be ready for that. But we're going to review some of that stuff, so it won't be the end of the world. So limit of a function, vector valued function. But like I said last time, sometimes it's really not too bad. So when I'm finding the limits, all I really want to do is plug and chug. All right, so we're going to apply the limit for each piece and see, just eyeball it really quickly and see if there's any part that would not exist. And then from there, we can make a determination of whether it's actually worth it to get into the process. But the limit as t approaches -2 of r of t would be us just replacing the t's with -2's, at least to start. So 4 plus 6, so we're looking at a 3. So 4 plus 6 minus the 1 is going to give us a 9 under the radical, so that's going to give us a 3i. Then 4 times negative 2 is going to give us negative 8, plus 3 is going to give us a negative 5, so negative 5j. And then the last part is a trig function, but that's nothing too crazy because if I plug a negative 2 in, I'm going to get negative 1 on top, so I'm looking at the sine of negative pi over 2 by unit circle trig rules. That's going to give us a negative 1. All right, so negative k. All right, and all this means is that we have vectors kind of going off in every which way when you plot this. I mean, when we did the elliptical helix, we had a bunch of different vectors that traced out the curve, all right? So what's happening here is as we get closer and closer to the t-value of negative 2, those vectors are converging on a particular vector, right? And so this appears to be that vector. All right, and so that's all we're really looking for. Now in the case of number 4, it's a little bit more elaborate because it's asking us in a procedural way to establish continuity. All right, because this is the 3-step process for determining if a function is continuous. Now, if it's going to play out, even for a vector value function, the first thing that needs to happen is the function needs to exist for that particular value of t. I'll get rid of that star. I forgot to erase it, so now I got to do it the old-fashioned way. All right, so plugging in a pi over 4, I'm going to get e to the pi over 4 times I plus sine of pi over 4, which is the square root of 2 over 2, j, plus the natural log of pi over 4. Times k. All right. Now, we're looking at a function that is not going to be continuous everywhere. It's not going to exist everywhere because of that natural log component. So if I'm just thinking in terms of the domain, I'll just kind of go back to that. It didn't ask us, but it was worth investigating. All right. Exponential function e is everywhere continuous. Sine function is everywhere continuous, but the natural log function is not. All right. Natural log function, natural log of t, and I'll just write, it really doesn't matter how you represent it. You could say z equals, you could say x sub 3 equals, or you could just say, here's my function f of t is equal ln of t. Only exists if t is greater than 0. Therefore, the domain of r of t, right? So r of t domain is going to be t such that t has to be greater than 0. All right, so that's something to take note of, because what that's telling me is that as long as t is greater than 0, it's not going to impact whether or not the function exists. All right, so it's not going to impact continuity. Pi over 4 is a value that's greater than 0. So that's telling me that if I want to find the limit of this, all I have to do is just what I did when I substituted pi over 4 into the original function. All right, so by direct substitution, I'm going to get the same exact expansion. All right, so for part C, when it's asking if it's continuous at pi over 4, well, the only place that we would have had trouble is if t were 0 or less. Pi over 4 is not one of those values where we would have trouble. So we could say it's continuous, but based on the process for continuity, you're looking to show that the function exists at the point and that the limit exists at the point in such a way that the limit is the same as what the function is at that point. All right. Bottom line is A and B have to be equal to each other, these two answers. All right, and they are. So yes, because now it's not really the most elegant solution to say A and B are equal to each other. So what I would say is the limit as t approaches pi over 4 of r of t is equal to r of pi over 4. All right. Very important because continuity implies differentiability. Right? If a function is not continuous, it's not going to be differentiable. So if I determined that the function is not continuous at pi over 4, then there would be no reason to take a derivative and plug in a pi over 4 for that derivative. Right? So it's definitely something to be mindful of. And I also enjoy the symmetry because I just went over this in my Calc 1 class today. In high school Calc 1, but still, you know, they just don't call it Calc 1, you know, but it's Calc 1. All right, so that's what we're talking about. We're talking about differentiability. And so what do I say? I say test for continuity first. If it's continuous, then you get into the process of looking for differentiability. But if it's not continuous, then you stop. All right, and so here it's continuous. So if we needed to take a derivative, at least we know we're not spinning our wheels for nothing. So the calculus of it is really just a reminder, like I was saying, that the limit definition applies. So that's all well and good. I'm not doing that, right? Because really what it is the limit definition of a derivative for each part separately. So that f of x plus h minus f of x all over h from Calc 1 for this piece, then separately for this piece, then separately for that piece, all right? It is the definition of a nightmare, right? So, not gonna do that, but what we can do is identify the domain, right? Looking at this, I see that there is considerations for the domain, and then I could also find the derivative. So, natural logs, any kind of log, you can't take log of 0, you can't take log of a negative number. So t minus 1 has to be greater than 0. All right, this part of the log. So that means t itself has to be greater than 1. All right, so we got that piece. The sine function I'm not worried about because the sine function is everywhere continuous. You can rely upon prior knowledge. Like you don't have to reinvent the wheel. If you know something is true, like polynomial functions are always continuous. You don't need to prove that every single time. Right? But the tangent is sine over cosine, so sine of e to the t over cosine of e to the t. Right? It's a fraction. So that means I can't have 0 in the bottom of the fraction. Cosine of e to the t, that cannot be equal to 0. All right. So for this one, it's a little funky because you're like, well, how the hell am I supposed to figure this out? You know, because we could say that cosine of pi over 2 is equal to 0 and every multiple of that. All right, so that's fine. But we also have to account for the fact that the inner function is e to the t power. So there's that component that needs to be addressed also. So there's a couple of ways to handle it. One way is to just rely on stuff that we did already, and that is that cosine is only going to be 0 when you're dealing with pi over 2 plus pi k. So what that would mean is that e to the t power cannot be equal to pi over 2 plus pi k. All right. But I still need to know what t can be. Now what e to the t can be. All right. How can I release that t from the captivity of the exponent of e? natural log both sides. All right, so we're going to take the natural log of both sides, and that's going to give us t cannot be equal to the natural log of whatever's on the right-hand side. All right, natural log of pi over 2 plus pi k. And again, I didn't write this out before because I knew I was going to write a bunch of other steps where k belongs to the set of integers. All right, so those are all the values that t can't be. Couple that with all the values of t that can exist, and you have your full domain. So all through this mess, we have addressed the restrictions on this function. All right, it will not exist for any value of t 1 or below, and then also anywhere where I have a natural log of pi plus pi k that falls in this interval, that's also going to be restricted. All right, so if you wanted to have a nice, I was going to say a nice, concise way of writing it. I don't know that you would necessarily call what I'm about to write nice and concise. I'll just say a way of representing your complete answer for the domain all in one expression. Squiggly brackets, I would be stating that my variable is t such that t is greater than 1 and t cannot be equal to the natural log of all that crap. All right, so you're kind of just getting it all in one shot. And normally I'd write the where k belongs to the set of integers, but I already wrote it, so I didn't include it. But yeah, that's hideous. But it's also stuff you have to keep in mind. Now, am I going to ask you to state the domain in every problem? No. But you do need to be aware of the domain. Because if I say find the derivative at a particular point, and that point doesn't exist, and you come up with a value, you're wrong. All right? If I say find r prime of 0, even if it gives you something in the derivative, the function doesn't exist at that location, so the derivative doesn't have any meaning there. All right? So now usually, if it doesn't work for the original function, it's not going to work for the derivative anyway, but there is that gray area. You don't want to fall into those traps. All right, so r prime. So I still have to do that. You know, you're like, well, that was a tough problem. Moving on. Well, now we got to answer the second half of it. Find the derivative. So each piece, we got a little chain rule for the first part. So sine of t squared, well, derivative of sine is cosine. So cosine of t squared times the derivative of the t squared, which is 2t. So that's my first piece. The second piece, I'm going to highlight the two factors that make up the product. Product as in product rule. So the first t minus 1 times the derivative of the second. So derivative of my second function, 1 over t minus 1, which will simplify, plus my second function, which is just the natural log of t minus 1, times the derivative of the first function, but with respect to t, the first function has a derivative of 1, so I don't really have to worry about that. And then for the last part, yeah, we need to know facts. What's the derivative of tangent? in general? Secant squared. So secant squared of e to the t. It's chain rule, so I have to multiply by the inner function's derivative. Derivative of e to the t is e to the t. Derivative of exponential function is the exponential function itself. All right, now if there's a constant multiple, you might have to multiply by that, but that's not the case here. All right, so that's actually our derivative. Now, in terms of level of difficulty, I mean, it seems pretty crazy, but really, if you think about it, it wasn't that bad. It's just a lot of stuff to write. I'm not big on making people simplify without cause. All right, let's just put it this way: if I ask you to find a second derivative, you're going to want to simplify, not because I told you to, but because you're not going to want to work with this expression in order to find the second derivative. All right. If I'm not going to make you do anything with the derivative, I'm not going to make you simplify it. All right. So you can actually just leave it like this. And in fact, I really kind of encourage you to, because what happens is people go rogue on tests, and it's not like it upsets me or anything like that, but it just makes it take longer for me to grade papers, because because I'm lazy. I'm just a lazy person. Right, I just want to put that out there. It's not always obvious, because sometimes it seems like I'm organized and stuff like that. But my whole existence is me finding ways to do less work. Right, so that's really all it comes down to. Right, so when I make an answer key for a test, I don't simplify it, because I'm like, well, I told them not to simplify it, so why would I simplify it? So all I do is I look at your paper, hoping that your unsimplified form matches mine, and then there's always somebody, will take it upon themselves to simplify their work down and come up with a beautiful, simple answer that I now have to determine if it is correct. I don't want to do that. It's a win-win for both of us when I say don't simplify, so don't simplify, all right? If you're told to, that's a different story, but I'm only going to tell you if there's a damn good reason for it to happen, all right? So that's just something to keep in mind. Derivatives of combinations of vector value functions of scalars. So this is where the rubber meets the road here, because we know that we could take the derivative of a vector value function because it's made up of other functions of t. And that, the process is not bad, but then it begs the question, okay, well, what does that mean? Right? Because a vector value function, go back to those graphs, it's the curve that's generated by vectors pointing out into space, right? So we got the elliptical helix, and it looked wonderful on GeoGebra, it looked terrible on paper, but it's based off of vectors. Each one of these components yields a vector. Then when we connect all those vectors, the endpoints of those vectors, we get the smooth curve. But by taking the derivative, I'm not necessarily getting what I think I'm getting, right? So we have to kind of flesh that out. But we also learned, and this is very important, that there isn't one type of product anymore. All right, back when it was just scalars, a product was a product. You multiply two things, you could use the x, or you could use the little dot, and everything was fine. But what we're dealing with here are vectors, and so that means that we could be dealing with the dot product between two vectors. We could be dealing with the cross product between two vectors. We could also be dealing with the scalar product, right? So, a scalar multiple of a vector, but we could also be dealing with some other function of t multiplied by a vector. So all these different ways in which you can multiply vectors, and each one has its own relationship. Now, they're all based off of the product rule in some capacity, but the meaning of these products and their derivatives is really what we're going to have to spend some time focusing on, right? So that brings us to the implication of zero derivative. So way back when you took a derivative and set it equal to zero and solve, like that was like your go-to maneuver in Calc 1. Man, I have no idea how to do this problem. All right, take the derivative, set it equal to zero and solve. It's probably the way to go, all right? Here it's a little bit of a different story. For a vector value function, if the derivative is equal to zero, that means, among other things, because you can have turning points at those locations, it also means that you could be dealing with a cusp in the curve at that location, right? So the only way you were going to get a cusp when you were dealing with a derivative, ordinary function derivative, was in the case where the original function existed, but the derivative of the function was undefined. All right? So function existed, derivative was undefined, and in that case, it could have been a cusp or a vertical tangent. All right? Here, when the derivative is equal to 0, that can potentially lead to a cusp. All right? The good news is you don't have to really flesh that out as much as you might have if you were in a class that didn't allow you to use the calculators. All right? So when in doubt, pop it in your calculator, and you might say, well, what about the h of t? Well, just do it for the f of t and g of t and see what's going on with that, because parametric form, you can put the x and y in, see what's going on there, because really h of t is just giving you the height. All right? So see what's going on with x and y. Maybe that's enough to give you a sense of what's going on with the graph overall. All right? We also say that a curve traced out by r of t is smooth on an interval if r is continuous and r prime of t is not equal to 0, except possibly at the endpoints. I'll address that possibly at the endpoints down the line. But it's kind of the opposite of what you would expect in function-based calculus. So all the single variable stuff that you learned back in Calc 1, it's kind of the reverse. All right? So when we're dealing with smooth continuous functions, we're talking about the derivative not being equal to 0. It's when you get into the corners, cusps, and things like that, that's when you're looking at the derivative being equal to 0. Next page we covered and talked about the rules, but those rules come into play on the next page. So, you know, I'll just do a little copy-paste job here so I can at least point to them. I like pointing this stuff. Reality is, I'm really just going to be talking about the same. At no point have we really talked about tangent lines or anything like that, because how do you find a tangent to a vector? Wouldn't the tangent be the vector itself? All right, because what we're going to need are tangents to the curve that exists at the endpoint of a vector. So that it's a little bit of a different story. So it's a change in the way of thinking. So I'm putting stars on these because really it's just a matter of applying the rules on the previous page. They're products in one capacity or another, but there is like little twists and turns that could kind of streamline the process for you. I'd rather you try to play around with that first before I give it all away. Product rule in each case every step of the way, but there are like little twists and turns that could be helpful. I'll get to that in a minute. Really got to unlink my son's phone from this. He's only 9 years old, so I don't have to worry about the pictures being too crazy. But when he becomes a teenager, this could be problematic. All right, so again, these are the 5 different versions of the product rule, right? Because we learned that there are different ways in which you could have a product. So here, I'm looking for the derivative of the dot product between R and U. All right, so one way to do that would be actually to find the dot product between R and U and then take the derivative, but I want to use one of these rules, all right? Well, I don't want to just use one of them. I want to use the appropriate one. All right. So first times the derivative of the second plus the second times the derivative of the first. What that's telling me is that along the way here, I have to figure out the derivative of R and U. All right. So that's what I'm going to do. I'm going to find R prime of t. It's going to be 6i plus 8t plus 2j plus 5k. All right, and u prime is going to be 2t times I plus 2j plus 3t squared minus 3k. All right, so the expansion of this derivative is going to be the first times the derivative of the second. So again, just going by the formula, it's not any different from what you learned in Calc 1. First times the derivative of the second plus the second times the derivative of the first. However, whatever textbook I copied and pasted this out of does derivative of the first times the second plus first times the derivative of the second. But different people learn in different ways. All right, so the only time it's actually gonna matter is when you get into the cross product, because we know that when you cross two vectors, that the anti-commutative property comes into play, right? So you don't want to mess around with the ordering on the cross product. The dot product doesn't matter which way you do it. So, but I'll follow the formula. So R prime U plus U prime times R. All right, so I'm dotting these two, or in each case, I'm dotting two vectors. All right, so I'm going to write them in component form. 6, 8t plus 2, 5 dotted against something a little bit more elaborate. T squared minus 3, 2t plus 4, t cubed minus 3t. All right, so that's the first piece. We got to dot those together. And then after that, we got to dot u prime against r. All right, so just a lot of writing. So 2t, 2 and 3t squared minus 3. Dotted against the original r, which is 6t plus 8. That lovely looking parabola, 4t squared plus 2t minus 3. And then 5t. All right, so let me just pop my little dot in there because I neglected that. I might have been just distracted by like whoever's screaming out in the hall. It's really only in the fall semester that this happens. In the spring semester, we kind of get rid of some of the dead weight around here, because like fall semester, it's straight up 13th grade for some people. They're going from like the way they acted like imbeciles in high school, and they just kind of carry that over into college without realizing that it's a different environment. But then they go away at some point. Oh, actually, they've already gone away. But what happens is they come back like right now, just to see if maybe they really aren't failing. Because they come for a couple weeks in the beginning, then they stop showing up. And then they'll come for a couple weeks right before the withdrawal deadline. You'll notice it in the traffic. Like a lot of traffic right in the beginning of September, then traffic dies down, and then there's a spike in traffic at the end of October, then it dies down again, because all those people who came back after a 6-week hiatus figuring, oh, I didn't have to go to class, because I didn't have to go to class in high school, and everything seemed to work out. It doesn't work out because they get their mid-semester reports, and it's like, oh yeah, not only are you failing, but you're impressively failing. So yeah, you might want to consider doing something about that. And what most teachers do is they give every strategy under the sun of like how you can recover, and the student interprets that as, oh, I should just drop the class. And so they do, and then they say, okay, I'll just take it again in the spring, and then they just don't come back until the following September, in which case the cycle starts all over again. Right? So in the spring, you see less traffic, you hear less people screaming like animals out in the hall, which I thought was just charming. You know, like a lot of different things come into play, but you see it like when you do this long enough. I've been here for almost 20 years. That I noticed the ebbs and flows, and it's mildly interesting, but distracting is probably more of an appropriate word. I'll allow annoying as well. That one's also an appropriate one. All right, so we're dotting these two together. So we're looking at 6t squared minus 18 plus, now I gotta distribute, so that stinks. I mean, it's not hard, you just don't want to do it. So we got 32t plus another 4t, so plus 36t plus 8. Then the last part at least is only distributing through a 5, just like the first piece wasn't that bad. So plus 5t cubed minus 15t. All right. And then in a minute I'll add that to the other mess, but while I'm here I might as well just clean it up a little bit. Get my like terms. So it looks like I have just that lone 5t cubed. It doesn't look like I have anything I compare with that, but I have two terms that have t's in it. So plus, t squared, sorry, 22t squared. Then I have the 36t minus 15t, so it's going to give me 21t. And then lastly, it just looks like because I already accounted for this one, so it looks like just a negative 10, negative 18 plus 8. All right, so that's that part of it. Now I just got to do all that crap again with this stuff. All right, but really it's just algebra, it's just distributive property. It's nothing too crazy. It's just you got to kind of knuckle down and do it. There are situations like in B where it'll actually kind of clean up sort of nicely once you get into the process, but you do have to begin the process in order to see that. All right, so for the second case, and I'll bring it all back in a sec. So I'm dotting these two together, 12t squared plus 16t. The middle one's nice because at least, I mean, there's a trinomial, but at least I'm only just doubling it. So plus 8t squared plus 4t minus 6. And then the last one, again, is just running through with a monomial. So plus 15t cubed minus 15 just t. All right, so this part I could also simplify. So I'll do that here. I'll just chuck a little plus sign here just to indicate that there's other stuff. So I got the cubed, 15t cubed. And I got my squares. It looks like 20t squared. Then 16 plus 4, 20t minus 15t is 5t, so plus 5t minus 6. All right, this ends up being one of those situations where like you're doing it on a test or something. Maybe you don't even check your work. If you're anything like me, you look at all this stuff that you just wrote and you're like, I don't want to do that. I don't want to do that again. So I'm just going to assume that I didn't just screw that up and just go from there. But now it's really bothering me that this stuff is so low. I should have moved it up a little higher. I forgot how to, oh wait, the cut and paste, yeah. Oh wait, that's not what I wanted to do. I want the plus sign too.
So if I erase the other thing, am I going to get stuck with that there in that location, or is it an object that I can now move?
I think you forgot a 14 on the left side.
I forgot a 14?
A 4T on the left side.
A 40?
A 4T. Like the middle,
620 plus 40 is the 20.
A 4D movie? Wait, what? Wait, which one?
when it's like 2 times 2T.
2 times 2t. Okay.
Shouldn't that be after the 36T? Or no?
Honestly, I have no idea. Let me see. Are you talking about when I distribute out the two binomials?
Yeah.
Bad boys? Okay, so 16t squared. Outer I got my 32t. Then I got 4t. Oh, I think I just combined it on the fly.
Okay.
Yeah, so it's there. It's just I didn't, for some reason, bother explaining it.
All right, so combining like terms, I got 20t cubed plus 42t squared plus 26t minus 16. Phew, Jackman. Yeah, that's something. Look at that. I mean, you'd be right in wondering, well, what is that? You know, aside from just a derivative. It's a rate of change of the dot product of two vectors. Now, dot product, it has meaning. You know, when you find the dot product between two vectors, you're finding a value of those vectors. It becomes a scalar. So this is giving us a rate of change of that dot product, but out of context, it doesn't really tell us too much. Without looking at a graph, we're not really analyzing it, but that's just a demonstration of the skill. All right, so in the case of the cross product, you know, it kind of plays out the same way in at least the early goings. But here I'm taking the cross between a function and its derivative, right? So really, I mean, I don't want to say it's math for the sake of math at this point, but it's kind of along those lines because it is, you know, what is the visual representation of the cross product of a function and its of a vector valued function and its derivative? That's something that we're going to talk about later, but for now, it's just another problem that we can do. So if I'm following the progression, you know, it's the derivative of the first times the second plus the first times the derivative of the second. I would write this as u prime of t crossed with u prime of t. Because the derivative of the first is going to become the u prime of t, but the second is already a u prime of t, plus the first times crossed with the derivative of the second. So the double prime of t. Well, that sounds exciting. Now, the second derivative, I mean, it's not challenging, because if I had to compute it, it's just taking the derivative of this again, and you're going to get some zeros in there because they have a constant, so that's nice. Everything gets simpler when you're dealing with polynomials. But as it turns out, we're not even going to get that far, really. Or we're not going to have to, we will get that far, but we're not going to have to bog ourselves down with a lot of calculations here, because the first component here is the cross product of a vector and itself. What happens when you cross a vector with itself? What do you get? You get the zero vector. All right. So now this just cleaned up to the cross of u of t and u double prime of t. All right. So we're never going to get to a situation in this case where it's challenging, because all we're doing is finding the cross product between two vectors. All right. So but what I would need to do is figure out what u double prime is. So that brings me back up to the top here, where I would just note it. U double prime of t is going to be equal to 2i plus, I'll write 0j just to have it, but then plus 6tk. All right, so that's getting crossed against the original function. So when I use my ijk notation, so I'm crossing u of t against u double prime of t, I, j, k. Well, I should give it a little more space because it's still an expression. All right, t squared minus 3 2t plus 4 and the last component is t cubed minus 3t. And then, I still need to look up there, 2, 0, and 6t. All right, so this is what I'm finding the cross of. So something I, something j, something k. So I'll write it below. Minus something j plus something k. Now there are some clean-ish parts of this where I expect some components to cancel out nicely. So maybe I don't need as much space, but I'm preparing for the worst. All right, so for the I, we got the downward diagonal giving us a meaningful product, but the upward diagonal is going to go to 0, so it's just 12t squared plus 24t. For the j, it's a little bit more elaborate, right? We're going to have 6t cubed minus 18t, but then I have to subtract from it that. So that seems like a little bit of side work. All right, so and just kind of chuck it off on the side here. So for the j calculation, I'm doing 6t cubed minus 18t minus the upward product, 2t cubed minus 6t, and then I could put the result in here. So 4t cubed, and then it'll be negative 12t. And then for the k, we could do that on the fly, because for k, we're able to take advantage of the 0 again. So downward, giving us a product of 0, minus the upward product, so negative 4t minus 8. All right, so like I said, down the line, we'll start talking about what a cross of a function, a vector value function and its derivative represents visually, but for now it's just a skill. But you see how this is way easier than it seemed like it would be going into the problem, because like by now you know dot products, easy. Cross products, I mean, I wouldn't say they're hard, but they're more involved, all right? It's kind of like, I equate the two as like law of sines, law of cosines. You know, back in Trig, when you came across the triangle problem and you're like, all right, I got to use law of sines, law of cosines. You're like, ah, crap, it's law of cosines. That's more work. I don't want to do that. Oh, this one's law of sines. I could burn through that really quickly. Dot product, you burn through it really quickly. Cross product, you know you're going to have to write some stuff. Right? So are you keen on doing that? Probably not, but you know that you can do it once you set your mind to it. All right? But it's nice to know that something like that is going to work to our advantage. But you don't know that if you don't know that, meaning if you don't recognize this as a property, the cross of a vector in itself going to 0, then you're on the hook for the work, only to find out that it's just going to end up being equal to 0. That's pretty frustrating. All right, so, you know. we've all been there. It happens. You go through the process. I'm sure there's definitely a video of me teaching this course where I just blew it. And I was like, oh, and we'll cross this, and nobody said anything, so I just did it. And then 15 minutes later, I finished the problem. I'm like, wait a minute, that was a cross of a vector and a sub. It went to 0. I didn't have to do any of that. And so, it happens to the best of us. Antiderivatives, same idea as derivatives. You're going to do it a piece at a time. So integrate, and we have the same idea with cross products. So with that being said, I'm just going to put a star on this because, again, I'd like to see what you can do with it first before I go through it all. So I'll go through all of these. I'm not going to leave it up to you to learn it on your own. I'd like you to try it first on your own before I bore you to tears with the explanation, which is me. All right, then we talked about integrals, and really just got to the idea of, just like derivatives and antiderivatives, we're taking the, derivatives and limits, we're taking the antiderivative a piece at a time. And that's as easy or as challenging as your comfort level as it applies to integrals. So the first one should be very easy, because it's the reverse power rule in each case. So t cubed plus t squared plus c. I'm going to designate that as you can go c1 or you could say c sub I. Most people, I think, are more likely to go c sub I to keep it consistent with the notation. If you're in component form, then you're more likely to go 1, 2, 3 instead of I, J, K. All right, but the reason why we have to sub it is because we're going to have 3 different constants for each different component. They're not necessarily going to be the same, so we have to account for that. All right, so then 3/2 t squared minus 6t plus c sub j. That's the j component, plus 6/4, so 3/2 t to the 4th plus 5/3 t cubed minus 4t plus c sub k, and that's the k term. All right. So it's not quite as simple as just throwing a plus c on at the end, because if I were to add something to the end of this, it would imply that there was another component to this vector, all right, putting it into the 4th dimension. And so the plus c's go for each individual piece. And that's going to play out the same way for each indefinite integral, but also it ties together nicely with definite integrals, where we apply the boundaries of integration to each component separately. All right, so if I were integrating on the interval of, let's say, 1 to 2, I would figure it out for each piece. Now, that being said, if we have a definite integral, it's going in the calculator unless it's something basic enough that you can do it by hand, or that you would be interested in doing it by hand. All right. So for part B, you can make these questions as easy or as difficult as you want based on your own personal experiences. Now, when I teach Calc 2, I go through all the rules and everything. We talk about use substitution, how to do it step by step, and then also integration by parts, how to do it step by step, and all, inverse trig rules and things like that. But then I talk about doing it on the fly. All right, doing it on the fly means, all right, let's say I know that it's going to be a U substitution problem, and I have a sense of what the U is. What I do is I just take a shot at it and see if I end up in the right place. All right, so for example, the reason I'm bringing that up is because this would be U substitution. I would define a U replacing the t squared, and the reason I would do that is because I know that the antiderivative of e to the x is e to the x, right? So
that t squared, if that were an x, or in the case of u substitution, a u, then I could easily take the antiderivative of it. So we let u equal t squared, all right? So if I know that that's going to be the case and go through the progression, eventually what's going to happen is part of my answer is going to involve an e to the t squared, all right? So then I check by differentiating. If I were to take the derivative of this, I would get e to the t squared times the derivative of the exponent, which would be 2t, which would be double what I want, right? I want 1t as my coefficient. If I take the derivative of this to check, I would get 2t as the multiplier. So what I would do is just correct for that. All right, I just slap a 1/2 on it and call it a day. All right. Maybe you don't like that. If you don't like it, unfortunately, it means you got a little more work to do. All right, because what you'd have to do is pull out your function, like off on the side here. I'd have to say x equals, or you could say f of t, it doesn't matter, t e to the t squared. Let u equal t squared. So du would be equal to 2t dt. Now ultimately I'm looking for an antiderivative, so I would use that notation. So the integral of t e to the t squared dt. This would become 1/2 du equals t dt, which allows me to swap out these two guys, making this 1/2 e to the u du, which integrates to 1/2 e to the u plus c, all for the purpose of just bringing it right back to what I got there just by taking a shot in the dark. All right. And, you know, you would say, well, taking a shot in the dark doesn't sound like a very mathematical way of tackling something like this. My answer to that is, well, you were tested on this in Calc 2. I don't need you to show me all this. I mean, you're welcome to do it. I don't need to see it. I need to see this. All right? I don't care how you get it short of cheating. All right? But you got to get from here to here. All right? All those integration techniques, that's why I'm so liberal with the calculator. I don't care. You've already been tested on it. I'm not interested in giving you an A in this course based on your knowledge of Calc 2. All right, it's based on your knowledge of Calc 3, but with the understanding that Calc 2 concepts are going to creep their way in here at some point. Just like Calc 1 did with the continuity stuff. It's all going to work its way in, but it's the path of least resistance that we're looking for. Right? So I'm going to say plus C1. And again, your subscript for C, it doesn't matter what it is. You can make it anything you want, as long as you're distinguishing one constant from another. IJK made sense here because those were the IJK components, but these are written in component form. So, you know, maybe you look at it and say, well, I don't have an IJK in there, so maybe it's the first dimension, second dimension, third dimension, all right? Sometimes you have a fact-based component, undo, and that kind of stinks sometimes because if you don't know what the antiderivative is of 1 over 1 plus t squared, you know, you could try to do a bunch of different things like partial fractions or use substitution, but it's not really going to get you anywhere fast. There is a workaround that involves integration by parts, but it's not convenient, right? So, well, I'll just ask you, does anybody know what the antiderivative of this is? Inverse tangent, yeah. Right idea, it's the right neighborhood. Natural log does also have that same kind of structure, but in order for this to have been natural log, the top would have had to be a 2t. All right, so the variable needs to be in the top, but if it's just the constant, then it's going to be an inverse trig function. All right, so we're looking at the inverse tan of t plus c2.
And just like I did on the previous page, I feel like I just boxed myself in here, so let me do what I did on the previous page and just cut this all out, move it, and erase. Now, yeah, that's a picture file now, so I can't edit it. All right, the last component, that's another U sub on the fly situation, where I would say, all right, well, if that 4t wasn't there, it would be the antiderivative of sine, which would normally, under normal circumstances, would be negative cosine. All right, so I'm going to type in. I'm going to pop in a negative and a cosine. I'm going to leave a little gap there because I know it's not just as simple as saying, well, it's just negative cosine. All right, I know there's going to be a coefficient there. It's just a question of what. All right, so if I take the derivative of this using chain rule to check, the negative cosine will become the sine of 4t, but then I have to multiply by the derivative of the inner function, which is 4. Making the derivative of this 4 times what I need it to be. So I correct for that. I pop in a 1/4. So just like the first component, you have a choice. You could try to do it on the fly, C3, PO. You could try to do it on the fly, and if it doesn't work, maybe you resort to doing it the long way. Because if I wanted to do it the long way, I'd have to let u be equal to 4t and just go through this entire process. Now, you can already see what the dilemma would be here. If you have 3 components, 3 is more than enough. I could have 4, 5, 6 components, that would be nightmarish. But 3 are enough, because if my 3 components are maybe one part is a general rule, like in the second component, one part is U substitution, the other part is like partial fraction decomposition or integration by parts, you could see how you could take a relatively basic, simple concept and make it something that is really just not that, right? So it is what it is, unfortunately, but and what it is reliant on your knowledge of some Calc 2 concepts. But really, if you think back to from the beginning of the course to now, how many instances, it's almost like I'm apologizing for this, how many instances have we come up against that were overly reliant on knowledge of Calc 2? Not too many, right? So it's bound to kind of creep up a little bit. This is one of those cases, all right? So for C, there's a cross product and an antiderivative involved. So we have to cross these two against each other and then integrate, right? So unfortunately, there's no reverse of the product rule, except to get into things like integration by parts. There are workaround techniques that you could use that are just different. I don't know that they're any simpler than just diving in and finding the cross product. So the I part is going to be t cubed minus t to the 5th. Minus the j part, t squared minus t to the 6th. And the k part, t cubed minus t to the 5th. All right, so we're anti-differentiating that, but after I found the cross product, it's really not that bad because it's the reverse of the power rule for each part. All right, so yeah, I mean, I could rewrite it, but I could also do something like this. Of course, the whistling sound is required. So 1/4 t to the 4th minus 1/6 t to the 6th plus c sub I, that's my I component, minus 1/3 t to the third minus 1/7 t to the seventh plus the constant for j. That'll give me my j component. And then the last part would be plus 1/4 t to the fourth minus 1/6 t to the sixth plus my k constant. And that's the k component. All right, so as antiderivatives go, you can see how it really wasn't, it didn't amount to much of anything in terms of difficulty compared to B. It was just reverse power rule. It's just we had to do it 9 times. 6 times. There's 9 terms, so yeah, that could be something. But and also really the difficulty level when it comes to reverse power rule is not anything crazy, because even if I had to figure out what the C values are based on some condition that was given, it's not going to be hard to do. All right, so that's good news. You get to something like this, it's all in the calculator. The only drawback is, well, there's a couple of possible ways that there could be a drawback. One would be if there's a discontinuity over the interval for a function. Now in this case we're fine, because everywhere continuous, discontinuous at multiples of pi over 2, right? But we never get to pi over 2, so it's not concerning, all right? So that's one thing that you gotta be mindful of. So improper integration might rear its ugly head. But with that out of the way, the only thing that makes this challenging is that I have to type in 3 separate expressions. That being said, I don't know, it's not that bad, but it's more like the second question, where you'd have to figure out what the antiderivative of tangent is, right? So you'd have to know that that's the natural log of secant of x, or you'd have to figure it out using use substitution. All right, the other two aren't bad because exponentially easy, and sine function, we kind of reviewed that when we talked about finding the antiderivative of sine of 4t, all right? So that would be kind of a repeat performance sort of thing. But math 9, good way to go here. Just make sure you're in the mode consistent with the problem. I had mine in degree mode. So all bets are off if you're not in the right mode. Really, I got to tell you, the only people in the years that I've been teaching this concept that have ever gotten this question wrong on the test, the only people who got it wrong because their calculator was in the wrong mode. So you pop it in, first component, points out, oh, that's shockingly simple. All right, so we're looking at 3/4. Now there's no plus c because it's a definite integral. I'm going to write this in component form instead of ijk. All right, so then I can do a copy paste, or second enter. Next part is tangent. You get that, which isn't the prettiest thing in the world, but if I want to try to make it look a little nicer, I could see if it's the square root of something. It looks like I'm kind of stuck with the ugly decimal, because it's probably a radical. I mean, it's most definitely a radical, but I just told you the antiderivative of a tangent function is the natural log of secant. So yeah, there's a radical in there, but you're also taking the natural log of it. Right, so to expect it to be the square root of something and come out cleanly is, not really going to play out as easily, right? You could actually convert it into exponential form, but now it's like, all right, well, why don't I just put the 0.693 in there? All right, then the last component is e to the negative 2t. And I'm definitely not expecting that to be nice. But that one, you know, like you can look at it and say, well, maybe I'll just do that one by hand because that one's easy enough. But maybe you don't want to.
I didn't get the 0.75 for the sine 2t.
And you're in radian mode?
Oh, that's what I figured.
Ah, there you go. All right, so that's cool. Oh, I forgot my X there. I think I'm gonna have to retype that in. Math 9. The negative 2x 0 and divided by 3 with respect to x. And make sure I typed it in correctly. And we get about 0.438. All right, and you know, like I said, with the other one, because it involves the antiderivative involves a natural log, this antiderivative involves an exponential base e. So it's not surprising that I get a decimal. Yeah, there are ways to convert it over into the other form, but more trouble than it's worth, right? Because just like I don't want to double dip on I stole my own thunder. On Calc 2 content, I don't want to double dip on pre-Calc content either. All right, so I don't want to spend time grading you for past classes. You know, I don't want that to get in the way of you demonstrating Calc 3 knowledge. All right, so if you got around, you got around. All right, but if there is a way to make it a nice clean answer, try. But if it doesn't play out within a couple of seconds, then stop trying. All right, because you're spinning your wheels for no reason. Right? Because I'm not going to look at your work and say, good, glad you did that. It made me happy that you spent 10 minutes converting from decimal form into a log form. It's not gonna brighten my day, right? So, and generally, since that's a good rule of thumb when you're taking a test, anything you do that's going to make me feel good is probably the way to go. So, what I've encouraged people to do is just write a joke on the top of the test, something that you think they'll find funny, and you know, it's automatic day brightener. I go into the test in a positive mood. Like, how could that possibly work against you? All right, so. But the last thing we're gonna talk about tonight is arc length and curvature. Well, just arc length, actually. We'll get to curvature next class. Curvature is actually a really fun topic. It's exactly what it sounds like. It's the idea that you can quantify the curviness of a function. Right? Some curves are more curvy than others. Right? So if I tell you that there's a number that will describe how curvy a graph is, you may not know what those numbers are, but you would imagine, I would think, that the number for a circle would be bigger than a number for a line, right? Circles are curvier than lines, right? Lines aren't curvy at all, so maybe the number for a line is 0, no curve, right? Maybe the small circles have a different number than the large circles, right? So these are some things that we'll get into. But before we do that, we need to talk about arc length. The good news is, it's nothing new. And that's why I can do it in a couple of minutes without rushing it. All right, so what we have here is a circular helix. All right, I know it's circular because the coefficient of cosine and sine are the same. All right, the elliptical helix, the coefficients would be different. All right. So when I'm looking for the arc length, it's really just as simple as taking our arc length formula from parametrics way back in the beginning of the first unit and just adding a third dimension to it. Right? So really, I mean, if you look at what we're dealing with here, it seems an awful lot like the concept of magnitude. And in fact,
under Solon, it really is a magnitude. You're looking for the magnitude of r prime. All right? So
so long story short on that, I like this formula better because I know what a magnitude is. And as long as I know what I'm taking the magnitude of, I'm going to be in good shape, right? And also, really, if you think about it, a magnitude's a distance, right? So if you're finding a distance between 2 points, you are finding the arc length of the line segment connecting those 2 points. So conceptually, it ties together very nicely. Now, they give us the start and the end point. So S is going to be on the interval of 0 to 2 pi. The magnitude of r prime of t, dt. So I just need r prime. So let me just jot that down here. So cosine has a derivative of negative sine. Sine has a derivative of cosine. And the last component is just a t, so that has a derivative of 1. I'm going to write the 1 in there. Normally I wouldn't bother, but I've seen it happen in the past. I haven't done a study on it or anything, but I don't write the 1. People all of a sudden forget this part in their expanded formula. Okay, so I include it there, and hopefully it'll remind you that that's still part of the fun. Right, so I'm going to find the magnitude of the squared values of each of these components. All right, so we're looking at, on the interval of 0 to 2 pi, the square root of negative sine t squared plus cosine t squared plus 1 squared dt. Now you could just pop this in your calculator, but this is one of those rare instances where doing it by hand is actually quicker than even typing it into your calculator. Okay, and that's because sine squared plus cosine squared is equal to what? 1. So under the radical, I have a 1 plus 1, which is 2. So this is 0 to 2 pi radical 2 dt. Integrating that, I get radical 2 times t on the interval of 0 to 2 pi. So 2 pi radical 2. All right, so like I said, you could put it in your calculator, but this is one of those rare instances that it's just easier to do it by hand. All right, so we'll be doing more with this starting next class. Number 2 is talking about the arc length of this function, which is raised to the 3rd power, which is a little beefier. So for this one, I would imagine you'd be more inclined to put it in your calculator because if there is a rule for cosine cubed plus sine cubed, it escapes me at the moment. So I'm going to go ahead and say that it's not overly likely that many people remember that either, right? And then the last thing here is the parametric equations for intersection of surfaces. I'm going to put a star on that and just ask you to consider it, not necessarily with the expectation that you're going to be able to go through the whole thing, but at least give it a little bit of thought, because when I go over it, I will tell you that you have all the knowledge and experience to be able to tackle this kind of problem. It's just, it's intimidating to look at.
right? And there's a lot of things going on, but at least if you kind of familiarize yourself with the structure of the problem, when I go over it, it's not gonna be, whoa, what the hell just happened? All right, so that's where we're gonna leave it for tonight. Just something to consider. Although, that one time I had a student spend half the class period trying to come up with a funny joke to write on their test instead of actually, taking the test. That ended up being problematic. Yeah, there's pros and cons to everything. All right, so then back to arc length, and we'll talk about arc length and curvature. So this one, we did the quote-unquote easier one, but it boils down to the same general concept, because the number one was easier, quote-unquote easier, because when I took the antiderivative, I was able to simplify, do it all nicely and elegantly, come up with a clean answer of 2 pi radical 2. Had I done that in the calculator, just typed it in as I saw it in the calculator, then the difficulty level between 1 and 2 is exactly the same. All right, regardless of the fact that we're looking at sine cubed instead of sine, sine cubed and cosine cubed instead of just cosine and sine, it would not make a difference whatsoever. All right, so one way or another, I need derivatives. All right, so that's important. And then I also need to actually find the magnitude of those derivatives. So when I'm looking at r, I'll just write it underneath it. It's going to be easier that way. R prime of t. Now the calculator understands derivative notation. The problem is it understands it at a point very easily, not as easily when it comes to generalized derivative functions. Right? So if you've had the notion in your mind of, well, maybe I'll tell the calculator to take the derivative of the function and then the antiderivative later on, I can say that sometimes it'll work and sometimes it won't. I'll show you how to do it in a couple of minutes, but it may not always work, and if that's the case, then you're spending a lot of time doing something that's not going to pay off for you. All right, so this is going to be in derivative form, 15 sine cubed t times cosine of t. The inner function is sine of t, so the derivative of sine is cosine. Then 9 cosine squared t times the derivative of cosine, which is negative sine. So I'm going to tack on a negative in front of the 9 and multiply by sine. The only saving grace on this one is that the last component t is going to go to 1. All right, so chain rule twice, and derivative of a linear function once. So still not crazy, but more than you probably wanted to do. So now what I have to do is find the magnitude of that. And instead of scrolling back and forth, I'll just throw it underneath. It'll make for some lopsided notes, but it's fine. So 0 to 2 pi, the magnitude of r prime of t is what I'm going to chuck into my calculator. All right. Now, you don't actually have to show me anything more on paper than the derivative, assuming that you're using this technique. That notation, I don't need you to write radical and then your x component squared plus your y component squared plus your z component squared. That's just a waste of time and energy, because the bottom line is you got to put that in your calculator anyway. Having you write it down is basically making you write it down twice, because once on paper and once in your calculator. If you write this down, I know you know what you're supposed to do. If you get the right answer, I know you did it right. If you get the wrong answer, I know you know what you were supposed to do. You just screwed it up when you put it in the calculator. All right? So either way,
you got enough for the bulk of the credit already. So, Math 9. On the interval of 0 to 2 pi, my x component squared, so 5 sine, I'm using x, squared. All right, that's how the calculator understands sine, oops, I said squared, but I meant cubed. That's how it understands the raising a trig function to an exponent. So sine cubed, if you try to type it in that way, it's not going to work. All right. Then we have cosine x. Then I got to close it up and square. Oh, actually, I never put the radical in. So let me just, I'm going to wipe it out and do it again because I'm just going to go back and try to insert stuff and I'm just going to botch it. All right. So I got to put the radical in. Then 15 sine, close it up, sine of x, close it up, then cube it, cosine x, close it up twice, then square it. All right, so that's the first component. Plus -9 cosine of x, close it up, square it, sine of x, close it up twice and square it, plus 1 squared, which you could just write as 1. All that, and then you hit enter, and you get that. All right, now, the trade-off, again, as you know, is it's either that or you do all that out by hand. All right, now sometimes, like I'll kind of split the difference, and on a test I'll say, write the integral that you would use in order to determine the arc length.
Shouldn't it be sine of x squared?
Oh, crap. Where?
When you took the derivative, you said the derivative of sine cubed was sine cubed.
Ah, crap an A.
I noticed that too, but I was like, should I say anything?
Yeah, sure. A likely story. All right, so let me go back and make that a square. Okay. All right, well, hopefully I typed in everything else right. And that's, unfortunately, I mean, I hate making my mistakes teachable moments because, unfortunately, over the years, there have been many, many teachable moments. But what we get from this is the idea that, dang, a minor slip-up could produce an answer that looks an awful lot like the right answer to the point where I didn't even question it. I just went with it because I was like, yeah, it's in the right neighborhood, so it's probably okay. So, yeah, there's that. Now let me show you the way that doesn't always work. But if it does work, you can save yourself a hell of a lot of time. All right. So that way involves your y equals. What you do is you type in your 3 functions as 3 separate equations. So 5 sine x cubed, 3 cosine x cubed, and then just x. All right, so all x's instead of t's. All right. This technique, if it works, gets you off the hook for having to find the derivative entirely. And if
if it worked in this case, then my mistake over there would have never even factored into the solution. All right, so I would have got away with it. It wasn't for those meddling kids. All right, so y1, y2, y3 are the actual functions. So what I'm going to do is go to Math 9. Still on the appropriate interval, 0 to 2 pi. Still need the square root. But instead of actually plugging in the derivative, I'm going to plug in a symbolic representation of the derivative. Right? So I'd hit Math 8. And then type in the derivative of y1. So alpha trace for x equals x. Close that up and square it. And then do the same thing for y2 and y3. Right? Because what it's going to do is it's going to, by points, figure out the derivative of each piece, square the results numerically, and then add it all together. The problem is if there's any break in the graph, the calculator is it's gonna freeze up. All right? Not freeze up as in you're gonna have a dead calculator on your hand, but freeze up as in give you an error or give you a nonsensical answer. All right? So Math 8, y2, alpha trace, select y2, x equals x. All right, it allows x to be a free variable, making it a function rather than a derivative at a particular point. Plus, I came out of the radical, let me get back in. So plus, open paren, Math 8. See the lengths we're willing to go to not have to take a derivative. And it's all in terms of x. All right, and again, the caution is sometimes it just doesn't work. All right, but notation-wise, really, if you think about it, each one of these components is saying take the derivative of what's in y1, y2, and y3. I plugged in my three components to y1, y2, and y3. So if anything was ever going to work on the calculator related to symbolic notation, this would be it. If it's not going to work, it's not going to work, but in this case, it actually works out beautifully. All right. Like I said before, if there's any kind of break in the graph, or if you have a circular logic issue, a reciprocal trig functions, forget it. Don't even bother. All right, so if you have like secant, cosecant, just don't even bother, because what's going to happen is you're going to get on that interval from 0 to 2 pi. If you have a derivative, let's say secant, the derivative of secant is secant times tangent. Bottom line is you're going to have a cosine in the bottom of the fraction. All right? And there are two instances on the interval of 0 to 2 pi where cosine is equal to 0, making it undefined. All right? So the calculator will never get past the part where the derivative is undefined for certain values of x. Right? So it would break apart. But if it works, then you just got yourself off the hook from having to find the derivatives. And the worst that could happen is, you realize, okay, well, I guess I have to do the work. All right, so that's the alternative. I guess I can just chuck it in here. At a minimum, it's a pretty cool function. That's really just a workaround for something that's already built into your calculator. Now, it's cool by TI-84 standards, because the reality is TI-89s, they just flat out find derivatives and antiderivatives for you, symbolically. Man, come on.
I just, like, why I can't get it to just lock into place? I know it's gonna move the minute yeah. Come on, you son of a gun. That's as close as I'm gonna get to. So I'm just gonna leave it like that. So either way, but we get the same value. Now, you may look at that and say, because before when I got the 22 point whatever, I was like, it looks about right. You might look at it and say, how did you know that? Well, I'm looking at the structure of the vector value function. Now it's made up of sines and cosines, so it has a circular concept to it. A unit circle would have been coefficients of 1, so that would have given me a circumference of 2 pi that were just a one turn around the circle, right? So that's my benchmark. That's my way of thinking. So this is somewhere between 3 to 5 times that value. So 6.28, somewhere between 3 to 5 times that value with some height. Like I can look at a circumference, but then I can also kind of pull it out into the third dimension. But the bottom line is, if I'm traveling around a circle a bunch of times, whether it's the same circle or whether I'm increasing by height, it's generally going to be in the same relative distance. All right, so somewhere between 3 to 5 times the circumference of a unit circle would put me in the 25 to 30 range. Right, so I knew that it would somewhere be in that interval. 22 was a little bit low, but it was not alarmingly low. Now you might look at it and say, well, okay, I would have never thought to do that. Well, fine. As long as you don't get a negative number, right? So let's start with that, all right? If you get something like 2.5 times 10 to the 32nd power, you did something wrong. You get a negative number, you did something wrong, right? So those are the things you look for the absurd values, that'll be your indicator. This is maybe a little bit beyond what you would consider, but it's not out of the realm of possibility that you could actually reason it out. All right. Now, number 3 is talking about the arc length for the curve formed by the intersection of the cylinders, this and that. All right. So what that's telling me is that first I got to find the intersection of the cylinders. All right. So now I included a diagram here, poor quality diagram, but it's surprising that this picture I grabbed from a textbook actually ends up being easier to actually discern than anything that I could produce on GeoGebra. Right? Everything I tried creating on GeoGebra, it looks great when it's an animation that you can play around with and manipulate, but on paper it just looks awful. Right? It didn't look anything like this. All right, but what I need to figure out are these lengths. All right, because we have 2 intersections. So where the curves are going to intersect, where the surfaces are going to intersect, they're going to create curves in space. Those curves are going to be represented by parametrics. Parametrics is just, a fancier way of saying vector value function, or maybe vector value function is a fancy way of saying parametrics. Maybe they're 2 things just trying to out-fancy each other. I don't know. But that's what we're up against. I have x squared plus y squared equals 9. So a circle with height makes a cylinder. And then y squared plus z squared is equal to 1. All right, so I have to parameterize this. I have to come up with the curve or curves that would represent the path of the intersection between these 2 functions. All right, I could do this using a matrix if I wanted to, because even though it's not linear, it's still the same structure as a linear equation. And I could use row reduction techniques and things like that. But I could also just do direct substitution. It's actually kind of set up for that. I have 2 instances of y. I got a y squared here and a y squared here. So I could solve one of these equations for y in terms of a variable in terms of y. So maybe I'll just grab, it doesn't matter which one you grab, I'll grab the second one. and it'll be z squared is equal to 1 minus y squared. All right. So z in terms of y. Okay, that's cool. I could also solve this one for x squared in terms of y. 9 minus z squared. 9 minus y squared. The only thing is I don't have anything for y squared, right? So you could look at it a couple of ways. One, you could designate y as being a free variable, right? It could be anything. Or I can try to put these two equations together in such a way that I could swap out a y in one of them and replace it with the other equation. So that'll give me a y in terms of x or a y in terms of z. But if these two equations are defined in terms of y, then that seems to be the path that I would want to follow, because what I can do is I can say that x, not x squared, but x is equal to the square root of 9 minus y squared. Now technically it's plus or minus. I could say z is equal to the square root of 1 minus y squared, technically plus or minus. And then I could let y be a free variable. Y is equal to y. Y is itself, right? The other ones are dependent on what y is, and so y is the one that has liberty to be free. Now, if I defined this equation by solving for z in terms, solving for y in terms of z, and then somehow solve for x in terms of z, then I could let z be the free variable. Or I could solve equations for y in terms of x and z in terms of x, and let x be the free variable. So there's really three ways that you could define your parametrics here, but the bottom line is this, in some way, shape, or form, is going to represent the path. Right? Now, typically we let it be in terms of t for consistency with the parametric model. So I'm going to let y equal t. And so my vector valued function r of t would then be plus or minus the square root of 9 minus t squared, t, and then plus or minus the square root of 1 minus t squared. All right, so that's the path. Now, it's a complicated path because there's two plus or minuses, which means that this could boil down to 4 unique possibilities. So r of t could be equal to the square root of 9 minus t squared, comma t, comma the square root of 1 minus t squared. Or it could be equal to maybe both are negative. Or maybe the first one's negative and the second one's positive. Or maybe it's the first one that's positive and the second one is negative. All right, so these are the 4 possibilities that emerge from this vector value function. Now, going back to the diagram, you look at it and say, well, maybe there's something wrong here because, I marked it up, but an intersection between two cylinders, you're going to have a circular intersection on one side and a circular intersection on the other side.
that seems to kind of imply 2 functions, but we got 4. Well, as it turns out, each one of these represents a half circle. Because if you think about it, in 2 space, if I wanted to graph x squared plus y squared equals 1, if I solved for y, I would get plus or minus 1 minus the square root of 1 minus x squared. The positive version would be the top half of the circle. The negative version would be the bottom half of the circle. Right? So here I have it for x and z. So, you know, you're thinking in terms of like when you're visualizing the coordinate system for x, y, z, 3-dimensional space, x is the one that's coming out of the page at you. So a positive radical for x is the front half of a circle. The negative is the back half of the circle. For z, it would be the top half of a circle for positive radicals and the bottom half for the negative radical. Right? So bottom line is we're getting a total of 4 circles out of it, 4 semicircles out of this, put it all together, and you get 2 full circles. But what we get even more importantly out of this is the idea that I don't need all 4 of them. All right, because that's what we were worried about, I think. Wait, am I going to have to do this process for 4 separate cases? No, you do it for 1 case because we're looking for arc length. Do it for 1 case, take your answer, multiply it by 4. Right? Because we're going to have 4 equivalent semicircles. Once you figure it out for 1 of them, then you have what you need. The issue that comes into play, and it's a significant issue, thinking to the formula, it's a definite integral on a to b. So there's that part of it. Where does it start? Where does it stop? All right, so let's take a look at the functions separately. So my components, I have x of t, that is not very visible. X of t, if I'm just focusing on this, is equal to the square root of 9 minus x squared, t squared, sorry. T is t, so I'm not worried about that. But z of t would be the square root of 1 minus t squared. All right. So it comes back to the concept of domain. I got to know where these functions exist, where it starts, where it stops in terms of t. All right. So that's what I'm going to do. If I take a t value that's in between -3 and 3, I'm in good shape here as long as I don't go beyond that. Like if I had a t value of 5, I'd get a negative under a radical. So t has to be between -3 and 3. And that's just number sense, number reasoning. Like you could set up equations and stuff like that, but really if you're thinking about it, I just want t squared to not amount to any value that's bigger than 9. So under what circumstances would that happen? As long as I stay between -3 and 3, I'm good. For the second one, as long as I stay between -1 and 1, I'm good. All right, but I need to satisfy both of them. All right, so the winner is going to be this one for my domain, because if I want to just satisfy this one, it could be anything in the interval of -3 to 3, but let's say it's 2, for example, then that would cause imaginary for this component, right? So that's no good, right? So if it's going to coincide between the 2 of them, it's going to work for both of them. But if it's only going to work for this one and not work for that one, all bets are off, all right? So now I know what my bounds are going to be. So I need the derivatives now, all right? So I need r prime of t. And that's assuming that you want to do it by hand, because, and this is really where that technique I showed you before has its benefits, because your calculators have histories, right? You can recall previous calculations. This calculation is not going to be any different for this question as it would be for the previous one, except for the bounds, right? So all I would have to do, instead of figuring out r prime of t, which, you know, it's not crazy, it would be just, I'll just detail it out here.
I could, instead of figuring out R prime of t, I can just put in my original R of t for x, sorry, y1, y2, and y3 and let the calculator do the work, right? But again, the caveat there is it's not always going to work. It's not always going to play out correctly, so you got to be careful, right? So you're looking at 1/2. Man, why did that happen? That's weird. Pen's still on. 1/2 9 minus t squared to the negative 1/2 times negative 2t. We can simplify that later. The y component was just a t, so that's going to become a 1. And the z component, same stuff, 1/2, but this time 1 minus t squared to the negative 1/2 times negative 2t. All right, so that's what would have to go into my, on negative 1 to 1, the magnitude of r prime of t, dt. So we'll try it in the calculator. If it doesn't work, it doesn't work, but at least we'll have tried. So 9 minus x squared, x, and then the square root of 1 minus x squared. All right. So you put those in. That's weird. Negative 1 to 1. And then hit enter. And it says, nah. Yeah, so in this case, it didn't play out. So we'll have to work it out this way. But the issue that comes into play is when you take the derivative, you end up with a 9 minus t squared in the bottom of a fraction. Right? Bottom of the fraction going on the interval of negative 1 to 1 is not going to play out the way we want it to, because if I plug it in there into my derivative, it's going to give me undefined, and the calculator just can't get past that. Right? So even though the area would exist, it just can't reconcile itself with that. Right? So the question that you might ask is, okay, is there a way that I could work around that? Right? And the answer is yes. Choose a value that's very close to the one in question, like 0.999, and see if it plays out. All right, because it's the one and negative one that are the problem. That's what's causing it to be undefined. If we can get really close to negative 1 and 1, then maybe it'll give us a truer sense of the area. All right, so then how do I know I have the most accurate version of the answer? Well, I don't. So let me try getting even closer to negative 1 and positive 1. If it'll let me. Well, it will. It just apparently didn't hit the 9 hard enough. All right. So 0.999 is as close as the calculator was willing to let me go without causing an error. So maybe you try 0.9991. You know, try to get as close as you can without causing the error. But there's a reasonable amount of certainty here that what we're looking at is approximately 3.1-ish. And that's for a semicircle. And we have 4 of them. And so we're looking at 12.3. All right, approximately. And approximate is fine, because the alternative to this, the alternative sucks. All right, I don't know how many of you remember improper integrals from Calc 2, but that was the case where you had one of the bounds of integration was infinity. All right, so you had to involve limits. What we would need to do is designate these bounds as, let's say, negative a and a, and I would find the limit. So after I find the integral by hand, substitute in negative a and a, simplify, then I would have to then find the limit as a is approaching 1, all right? And hope that that gives me something near what the correct answer is. So this is a nice numerical workaround for it, because I know that if I can get close enough to negative 1 and 1 without actually getting there, then I'll get a sense of what the area is approaching under the curve. And if that's the case, like a limit would be what it's approaching anyway, so that would be sufficient to get the job done. We were parameterizing in terms of time, all right? So we were establishing that the position along the curve, any kind of path, was based on passage of time, all right? So what we want to do here is parameterize in terms of the arc length, which means that the position in space is based on how far you've traveled along the curve, all right? So I'll just give you a quick example, and just a diagram off on the side. I don't even know that you have to copy it down because it's not going to be pretty, but it's the best I got. I mean, the act of me producing the diagram is not going to be pretty. The concept should be fine. All right, so. All right, so you got some paths, yeah, so terrible diagram, but that's not really what it's coming down to. It's more so, and I'll just even keep it on the surface. So some origin point on the y-axis. All right, so we could parameterize this function in terms of time, which would be to say after 10 minutes, where are you along the curve, right? But when we create parametric graphs, what we're vector valued graphs, what we're determining are vectors that trace out the curve itself, right? So let's say I'm just focusing on these 3 vectors, all right? So the t value is related to the movement of the vectors, not the movement along the curve, right? So these vectors are going to have angles that separate them from the xy plane, separate them from each other, and those are based on the passage of time, right? So this would equate to the idea of you're standing at the base of a mountain or a trail, and there's a hiker moving along the trail, all right? As that hiker moves along the trail, you're standing at some fixed location, and you're just keeping track of time, all right? They have a position here, here, and here. All you're going to get when you parameterize in terms of time is the change in their position relative to your location, all right? Now, change the perspective of the individuals and forget about the person at the fixed location, because I don't know about you, but I don't often have a person standing at the bottom of a mountain or a hiking trail just keeping track of my progress, all right? Generally what's happening is you're on the trail yourself and you're keeping track of your own progress, all right? So this individual is moving along the path. That movement is going to create an arc length, all right? So what I would want to do sometimes is define my position within this whole system based on my individual movement along the path. All right, so arc length S would define my movement along the path. And so my function, instead of R of t, I would want to have a vector valued function R of S that's in terms of movement along the curve. All right. So you could expand it to a bunch of different ideas. Driving in a car, you're following some navigation app, Waze or whatever, and imagine that your progress along that app is, that information is given to you based off of your movement relative to some fixed location, all right? So some satellite orbiting the Earth and where you are relative to that satellite, all right? So if that's the case, then things could get pretty confusing very quickly because you'd be receiving information in terms of latitudes, longitudes, and distances away from that satellite, right? So you would actually get cylindrical coordinates representing your location. Rather than saying that you traveled 10 miles, it would say something like you traveled 30 degrees. Well, that's actually hugely inappropriate. You've traveled like 0.03 degrees by 0.03 degrees by 50,000 miles, all right? Because what's happening is your position is based off of a change in latitude, longitude, and then your distance relative to the satellite, the Z, right? So that's not information that you'd find valuable if you just wanted to know how many miles it is to the nearest gas station, all right? So parameterizing in terms of arc length has a lot more meaning for us if you're looking to conceptualize in terms of real world situations. Now, in terms of actually carrying out the process, you can see, I mean, we got some nice formulas here, but the formulas themselves are really just dictated based off of our knowledge of arc length, right? So we have an arc length formula, but what we need to do is create an arc length function, right? But a lot of what we're gonna do is gonna be very, very similar to what we've done before, right? So let me take you through the arc length parameterization for a parabola. And so what this will do is instead of giving us movement based off of distance from the origin, it'll give us movement relative to position within the parabola, the surface of the parabola at any particular moment. All right, so first step in the process, find the derivatives. Now, no calculator bailout for this one because it's going to be symbolically represented. It's not a definite integral in the sense that it's not going to be numerical, all right? Or at least not entirely numerical. So let me figure out r prime of t, which in this case is going to be 2t I plus 1j. All right, so we have our two components. What I'm going to do is set up an antiderivative going from some initial t value. Now, we weren't getting, you know, like if you jump to number 5 here, you can see that the t's are defined from 0 to 2 pi. That makes life easier. Here it's not defined in any particular way. So you might say, well, what do I do? T sub O to t. Well, we're leaving the top t completely variable, all right? Because what I want to have is an arc length that is an arc length function. So it allows for the arc length to be variable depending on what my value of t is. But I got to start somewhere. Since t typically represents time, what I would do is I would establish the lower bound to be some constant. The most appropriate constant seems to be 0 unless you're told otherwise. All right, so 2t squared plus 1 squared dt. All right, so I have to integrate this. I can simplify it a little bit first, though. So 4t squared plus 1 dt. All right, so I'm integrating that on the interval of 0 to t. I'm allowing for the flexibility of the upper bound to be, I'm allowing to be anything. All right, there's no limit to it. So the further I want to go out on the parabola, the more arc I'm going to cover. All right, and that should make some kind of sense. If I only wanted to go out
for 5 seconds, then I would only get a numerical arc length for 5 seconds. But if I want to have a function that's going to represent my arc length for any time t, my upper bound, just getting back to the fundamental theorem of calculus, so Calc 1, that needs to be an upper bound that is variable. I lost the word there for a second. Right, so anyway, I got to integrate this. I mean, that's really what it's coming down to. And it stinks because it involves having to carry out a process that maybe you're not overly keen on doing. All right, now there are rules that you can memorize and stuff like this, but this has the look of an inverse trig function. It's very similar in structure to an arctan, but not quite. All right, so we have to go back to trig substitution in order to integrate this. All right, so I'm gonna just pull out the relevant piece, the integral. Let me just I'll strip it down. I don't even want the bounds. So 4t squared plus 1 dt. We need to pull out our u's and a's. So I want to substitute in a trig function that hopefully will be easier to anti-differentiate. All right, and that trig function should have, the ratios that I create should lead to that radical being part of the triangle. So the u's and a's that come from the radical itself, I'm just trying to give the short version of the explanation. The u is going to be the square root of the first term, and the a is going to be the square root of the constant term. So it's in this case that the u is the square root of the first term. It's the variable term that has a root that's equal to u, and the constant term that has a root that's equal to a. We want to put these in the triangle so that using the Pythagorean theorem, the third side would become the radical itself. All right, so I'm going to place the 2t here and the 1 here. And if I find, using the Pythagorean theorem, the hypotenuse, that should end up being the radical. Square these, add them together, and slap a radical over it, and you will get that radicand, or the integrand. All right, so that's my triangle. What I want to do is define a trig function that's going to allow me to swap out all this nonsense. All right, so the first one is going to be the ratio of u over a. Yeah, if we're assuming that this is my reference angle, u is the opposite side, a is the adjacent side, so that makes a tangent function. So tangent of theta is going to be equal to u over a. So tangent of theta is equal to 2t over 1, so just 2t. The secondary function should be the ratio of the radical to the constant. All right, so like I said before, I try to minimize the amount of Calc 2 that's in here, but some things we can't avoid. And it's almost like, in this case, it's like you're trying to save us from Calc 2, but now you bring back the worst part of it. Radical to it's unavoidable. You know, it comes up in some cases. But we have hypotenuse over adjacent, so that's the secant function. All right, that's going to allow me to swap out the radical for a secant of theta. But I also have to get rid of the dt here. So I'm going to manipulate my tangent theta equals 2t to make it t
equals 1/2 tangent of theta, and then take the derivative of that, and we end up with dt equals 1/2 secant squared theta d theta. All right, so it seems kind of surprising that somehow out of this mess we're going to actually come up with a substitution that's going to be meaningful, but it's actually going to happen. It's just not the most comfortable process in the world. All right, so in my integral, I'm replacing the radical with a secant theta, and I'm replacing the dt with 1/2 secant cubed d theta, theta d theta, squared. It'll eventually, the next step, it'll become cubed. Theta d theta. Oh, one step ahead business. So 1/2 secant cubed theta d theta. All right, so we're going from something that we had no chance of anti-differentiating to something that at least we have a fighting chance of anti-differentiating. More than the fighting chance. I mean, we're going to be able to do it, but there's still a little bit more that we have to carry out. All right, because it's not like you can just apply the reverse power rule and call it a day. It's not a power function. All right, so what we have to do is involve a trig identity substitution now. Right, and so when we do that, we can actually make a substitution for secant squared theta. There's a relationship between secant squared theta and tangent theta, tangent squared theta. Anybody happen to remember what that is?
1 plus tan squared?
1 plus tan squared, exactamundo. All right, so now if I distribute into this, and it doesn't seem like we're getting anywhere in a hurry, but if I distribute into this, I'm going to create a secant theta, which is going to actually anti-differentiate itself by rule. All right, so 1/2 secant theta plus 1/2 secant theta tangent squared theta, all d theta. So this part will integrate by rule. The other part we still have to play out. All right. So then it becomes a question of like, how do you want to play that out? All right. So the first part, 1/2 ln secant theta plus tangent theta plus the antiderivative of 1/2 secant theta tan squared theta d theta. Now again, you think back to what we started with, you're like, wow, this got ugly in a hurry. But it's not a question of getting ugly or being concise, because I mean, you compare this to what we're ending up with here. This looks nicer, but you can't do anything with it, right? That's the problem. Now you stare at this for half an hour and you get nowhere, right? Now maybe you convert it over here and you stare at it for half an hour and get nowhere, but that's a different conversation. But at least we got to a point where I could take the antiderivative of the secant of theta.
Now I need to figure out what the antiderivative of secant times tangent squared theta is, right? Because then, once I do that, I can go back in and start substituting, right?
Because I got to get it back in terms of t after the fact, right? So that ends up being the other challenge, right? So you got to think about what we can do here. And when it comes to integrating, we have choices. We can take a shot in the dark and hope for the best, or you can start progressively going through your different options. First option would be u substitution. So can I define a u that's going to work? Well, if I let tangent be my u, that'll create a secant squared. That's no help. If I let secant be my u, then that's going to create a secant times tangent. So that's no help. All right, tangent squared, that's going to go off the rails very quickly. All right, so then you look at it and say, well, maybe it's not that. Maybe it's integration by parts. All right, maybe it's some other technique. All right, so what I'm going to ask you to do is try this part on your own, because there's no point in me just carrying through the process of integrating it for you if it's just not gonna, I don't wanna say it's gonna fall on deaf ears, but it's, let's see what you got. If you can come up with that, then I can take you the rest of the way, all right? But I want you to try that on your own. And then and I'm also looking at the clock too, so I don't wanna keep it any longer. Then after that, the other problems, you look at it and say, well, if that's number one, we're screwed when it comes to some of the other ones. Yeah, totally. Yeah, it's all over. It's the end of the world. No, I chose this problem to make you appreciate trigonometry, right? Because it'll be shocking how easy 5 and 6 and even 7 are in comparison to this one. Now this one has simple algebraic components, so you say, well, if anything's going to be the easy one, it'll be this one. This is the hardest one. These ones actually end up being really nothing at all. Like I'll just put it to you this way. The amount of space that I gave for numbers 5 and 6 are appropriate for numbers 5 and 6. All right? As you can see, not nearly as appropriate for number 4. Right? But I wanted to show you the worst case scenario. And honestly, I feel like I may have proved my point just by getting this far. But I do want to see if we can come up with that. At least that component. And then we'll pick up with that next class. All right. So almost done.